Well, thank you for the introduction, Tamara. My name is McEvoy. I'm a climatologist. Research is heavily focused on drought and snowpack and weather and climate, and a lot of that focuses in the Great Basin and the Sierra Nevada. So today I'm going to kind of give you guys an update on what's been going on the last few years, this current water year, how the winter's starting, and kind of give you a sense of what we know and what we don't know about in terms of a winter forecast. And so this picture is actually from last year that I took. This is from the base of Mount Rose Ski Resort on the slide side. This is on New Year's Day of 2018. And so we were off to a really poor snowpack start, and we had a pretty poor snow year for most of the year last year. And so you can see at 8,000 feet, there's no snow on the ground there. There's some snow on the north-facing slopes, but we had a really poor snowpack last year, and luckily we're doing a little bit better this year so far. And I wanted to show this. So we're here in Reno under gray skies today, but this is a very shallow cloud deck that's out there right now. And if you're lucky enough to be above that in the mountains today, this is again from Mount Rose Ski Resort. It's a beautiful sunny day up there. So we get this quite often in the winter where we have the low-level clouds, and then you go up to the mountains and you're skiing in the sunshine. So pretty nice out there today. So I wanted to start off with a snapshot of drought conditions from the U.S. Drought Monitor. Dave Simmerall's here, and he's going to be going into detail on exactly how these maps are created. And so I'm not going to go into all that detail other than saying there's a lot of information, there's a lot of data, temperature, precip, snowpack, reservoir levels, stream flow, there's impact information, there's professional judgment that go into these maps that come out once a week and give a snapshot of the current drought conditions. And so this was the one that just came out this morning for the western U.S. And what we see for our region is that, so anything in white is no drought at all. Yellow is abnormally dry, which is D0, and it's not actually considered a drought category. That's you're kind of going into drought. And then the browns and reds are the drought categories. And so for us, we have a large area of yellow in the center of Nevada, which is abnormally dry, so no drought classification there. And there's a small sliver in the eastern Sierra. I believe that was just changed this week from an abnormally dry to no drought to no category at all. So we have that white sliver. And then there's a big portion of Nevada that's in moderate or even severe drought in the northeast corner. So I'm going to kind of walk through on how we got here and where we've been with drought and wet cycles over the past several years. And I'm going to start out by talking about some of the recent drought cycles that we have. And so this is another image from the U.S. Drought Monitor, and they have a nice tool on there where you can actually make time series of a given area that shows the percent area in drought. And so this is a time series starting on the left from 2000 when the U.S. Drought Monitor started, going all the way to present. And so the y-axis is the percent area, and this is for the Truckee River Basin. And so if there's colors all the way to the top of the graph, that means the entire basin was in some form of D0 to D4. And if there was, let me get this here. If there was some of these where you have white going about 3/4 of the way up, that would mean the basin's in about 75% of the basin's in drought. And so then the colors are the same as on the previous slide. And what we see here is that, the main thing that we've been seeing is that over the past 18 years or so, we've been in drought a lot more than we've been out of drought. And so there's a lot more yellows and reds and browns than there is white on there. And so, and our recent pattern from about 2017, since our record-breaking precipitation year, since then, that's actually been one of the longer stretches in the last 18 years up until now that we've kind of been out of drought. And so, does that mean we're entering a wetter pattern? We can't really say right now, but it is one of the wetter times in the last 18 years or so. And so, this is the same graphic, but for the Humboldt River Basin in central and northeastern Nevada. Similar patterns with different levels of severity, if you kind of go back and forth, where the 2012 to 2015-16 drought was still showing up, but not as severe. And I believe the earlier drought in 2000, the early 2000s was more severe in the Humboldt Basin. And this is the same thing. We're kind of seeing this cycle of 1 to 3 years being out of drought, and then longer cycles of 3 to 5 years or even longer of being in drought. And so this is really a pretty short-term perspective, only about 18 years or so. But we can look at a bit of a longer perspective. And I say longer-term droughts because this goes back to 1895. This is based on PRISM data, which uses weather stations data across the western U.S. to make gridded maps of temperature and precipitation. And I say longer because this is our instrumental record that goes back, 125, 150 years. There's a much longer paleo climatology record that goes back thousands of years, and so this is really still in the grand scheme of things, it's kind of a shorter term, but for our instrumental record, this is what we got, about 125 years. And this is the standardized precipitation index for the Truckee River Basin. And so each bar represents the water year, 12 months ending in September. And these are normalized anomalies, so the black line going across the middle is average. Anything red is below normal, and anything blue is above normal. And so this is kind of the time period that was showing up in the U.S. Drought Monitor from 2000 to present. And you can see that there's a lot more red bars than blue bars there, but the couple decades before that were actually very wet. In the 70s, 80s, and 90s, we had a lot more blue bars than we did red bars. And then there's kind of been this cycle of about 10 to 30-year periods of wet and dry cycles in the region. And the black line there is a smooth 11-year average. And so you can see that's kind of oscillating up and down. And there's really no trend up or down in terms of long-term precipitation patterns. But where we do see a trend is in the temperatures. And the temperatures have a very, very large impact on drought. And so this is also for the Truckee River Basin. And this is also the 12 months ending in September. And the black line is the average. And so we've seen this steady increase in temperatures. And this has really been noticeable since about 1980. We see the smooth 11-year curve really start to increase, and it really hasn't stopped since then. And 2015 really stands out as the warmest year in this record. This past water year, 2018, was one of the top, looks like top 5, and we keep seeing this pattern every year is showing up as either the warmest year or in the top 5 year after year. And so this has a big impact on drought in a lot of different ways. 2015 was record warm. It was dry around here, but it wasn't a record dry year in terms of precipitation, but it was a record low year in terms of snowpack. And that was because of the warm temperatures and this idea of snow drought, which I'll talk a little bit more about, and how you can have go along having average precipitation, but still have much below average snowpack because of temperatures, and that contributes to lower runoff, higher evapotranspiration during the summer, drier soils. So there's all these negative drought impacts related to the warmer temperatures that you don't see just by looking at precipitation, which really there's no trend showing up there. And so there's some indices out there that combine temperature and precipitation into one, and this is the standardized precipitation evapotranspiration index. Instead of just looking at precipitation, it looks at the difference between precipitation and evaporative demand, which is the thirst of the atmosphere or the drying power of the atmosphere. And the model used here, it only uses temperature to compute the evaporative demand. And so this doesn't look, first glance, it doesn't look all that much different than the first graph I showed of just the standardized precipitation index. But when you start to look at, again, since about 1980, you see this strong downward trend. And in the first graph I showed there, the past 4 years were all near normal or above normal precipitation. When you factor in the temperature and the evaporative demand, only the big year of 2017 was above normal, and all these other years are still far below normal with this drought index. And the most severe drought years have occurred all within the last 10 years or so. So there's lots of temperature-related impacts showing up. So I want to talk about more recent, just this past water year, which was September October 2017 through September 2018. It was a pretty interesting year, and so this is the temperature percentiles and the precipitation percentiles. So these basically, this uses PRISM data, so you have a record going back to 1895, and what this map is showing on the left is anything in red is the driest water year on, warmest water year on record going back to 1895. Anything on right, the red is the driest and the green is the wettest in the entire record. And so in terms of temperatures, we saw that continuing trend of a very warm water year. It was really pronounced in the Colorado River Basin and the Four Corners region. They all saw record warm temperatures. And our precipitation water year was really pretty interesting. In the eastern Sierra and the northwest part of the Great Basin, there's a lot of white and that first shading of green. So white is kind of near normal, kind of an average precipitation year. And green is a bit above normal. And it was much drier into the eastern portions of the Great Basin, where they're in that bottom 10th percentile, bottom 10% of the distribution. But when you actually break it down into the individual months, and then actually the daily time series, which I'll show, really we had our precipitation come in a few waves. So if you look at this is the same set of maps, but just for the winter, just December through February. And so temperatures don't look that much different. It was pretty much warm across the whole region, above normal, top 10% in a lot of locations. But we had an extremely dry winter, which is when we get most of our precipitation around here. And there's even some red dots showing up there indicating the driest December through February on record. And this is also our season when we get most of our snowfall. And so when you look at it kind of going throughout each day throughout the water year, this is from Tahoe City, up at Lake Tahoe, and this is showing the accumulated precipitation starting October 1 of 2017. And the brown line is the average, the 1981 to 2010 average. And so we had a few interesting events. We had a very large storm in the middle of November last year that brought upwards of 4 to 6 inches of precipitation. It was a very good storm, but it was warm and it didn't produce any snowfall at the lower elevations. I remember last year, Mount Rose Ski Resort, from that storm, they got about 4 feet of snow, but places like Squaw Valley and Alpine Meadows at the base and the lower part of the mountains, they got all rain, so they had no snowpack accumulating. Then we went into winter and the line's pretty flat all the way through until right around the beginning of March. There was hardly any accumulation. If you compare the green line there to the brown line, we're far below normal there at the end of February. Then we had a very welcome wet March where we had several large storm cycles that brought us pretty near normal precipitation in the matter of a month, and then it kind of dried out again where we didn't really have a lot of big storms except for a decent storm in early April. And you can look at the same thing, but this is the accumulated snowfall now at Tahoe City. And this is kind of the elevation that's really seeing the biggest impacts of climate change on snow conditions, kind of that 6,000 to 7,000 foot elevation or 5,000 to 7,000 foot elevation. And a lot of the watershed in the Tahoe Basin and the Northern Sierra and parts of the Great Basin are at these kind of mid-elevation ranges that are very sensitive to changes in temperature. And so you can see the November storm brought no snow accumulation at all to Tahoe City. They had a little bit in, not much in December. January they had a little, but March they had a ton of snowfall, nearly 100 inches of snow in Tahoe City in 1 month. But when you got to April 1, which is kind of the peak snowpack, there's still about 70% of average. So it still wound up as a below average snowpack year. And we can look at this spatially across the Great Basin in California. And so this was the percent of normal snow water equivalent from the NRCS tools from March 1st. And so anything in brown or reds is below normal. And so the entire area was below average and in very poor shape. Most of the region was in about 40 to 60% of normal. snow water equivalent. And then we had March, which I'm kind of calling miracle-ish March. There's this term miracle March that came about many years ago when we were in a similar situation that really brought the snowpack up to above normal after being very dry. And so this was, we would have been in a very, really bad situation if we didn't have this March. And it improved the snowpack a lot, but even on April 1st, the snowpacks in the region were 65 to 80% of normal. And so it was very welcome, but we were still below average in terms of snowpack for the water year. And I mentioned that term snow drought and this concept of a warm snow drought where you can have precipitation that's near normal, but because of the warm temperatures, the snowpack can still be very low. And so this is one example. This is from last year again. And so each one of those dots are a snow sampling location in the Lake Tahoe Basin. And on the x-axis, we have the percent of median snow water equivalent going from 0 to 120. And then the y-axis is the station elevation. And so we have kind of these lower elevation stations below 1,800 meters going all the way up to 2,600 meters. So a good range of elevations. And the dots are colored by the percent of average precipitation. And you'll notice all the dots are white, indicating that they're all within this 80 to 120%, or kind of normal precipitation when you consider the entire water year. But the lower elevation stations were about 50 to 70% of median snowpack because of more precipitation falling as rain instead of snow. Then when you got higher up, the snowpacks were actually in decent shape, and there were a few that were kind of in the 80 to 100% range. So we're seeing this strong elevational gradient setup during a lot of these snow droughts, where the lower elevations get impacted a lot harder, and the higher elevations are still kind of doing okay. And if anyone has questions during this, feel free to interrupt me and chime in. Sorry, I should have mentioned that before. So we had our snowpack kind of near to largely below average throughout most of the region. And then throughout the summer, we had a continuing trend of hot summers, above average temperatures throughout the summer. And this is a temperature percentile map for June through August of this past summer. Lots of dark red indicating the warmest summer on record, going back to 1895. Not quite as bad in the north, but still in the top 10%. So this is still a very much a warm temperature anomaly for the summer. And I pulled out a few time series from different locations. This one's from Reno, goes back to 1937. And these are the average summer temperatures for each year. And again, we're seeing this continued trend of, every summer now is the hottest, or very close to the hottest on record. This year, 2018, was the second hottest for Reno. 2017 was the hottest. And if you look at the actual temperature values, this is a really big change. This period in the 40s through to about 1970, we had mean temperature values about 65 degrees. Since 2012, we haven't been below 75 degrees for the mean temperature. So these aren't small changes. These are a really big warming trend showing up. And same thing in Las Vegas. This year was the hottest on record. 17 was the previous record. 16 was the previous record before that. So we're kind of just we're getting close to breaking these new records every year now.
I got a question.
Yeah.
With the recent fires that we had last year, did that have an impact on temperature as well too, with all the smoke that we had from the valleys for maybe a couple months?
If you're in a region that is consistently in a smoky pattern for...
When we were down Gardnerville, our AQI was over 400. We had a lot of smoke from the fires.
That can actually cool the temperatures due to the not as much sunlight getting through. That's the main impact of smoke. If you have thick smoke for a long period of time, you can actually see cooling below normal temperatures.
Okay, that's one of the smoke.
Yeah. And most of the fire scars actually make the land surface temperature much warmer too. And so you have definitely varying impacts from fires on temperature. And so I wanted to now get to kind of how the previous water year the summer, and how that's, what that wound up doing for our water supply and our hydrology conditions around the region. And so this is a time series going back to, I think I selected this because this is the same period as the drought monitor, about 2000. These are the lake levels at Lake Tahoe. And so Tahoe is a very large reservoir. It is managed and controlled, but it still does a great job of showing natural dry and wet cycles, and you can really see that here. And it's a large reservoir. It takes about 3 or 4 years to actually respond to get to severe drought conditions from when it's full. And so we see some cycles here. And so the red line is the natural rim, and that's the elevation of the lake where water can spill over into the Truckee River. And so anytime you're below that red line, there's no water flowing into the Truckee River. And that's about the most severe kind of drought you can be in, considering Tahoe. And so here we are today. So we have this recent wet cycle. Then we had our really bad drought cycle starting in 2012. And so 2011 summer, or 12 summer, the lake was pretty full. And then we had a dry year 2012, 2013. Even after two pretty bad drought years, the lake was still kind of around average, and it wasn't all that low. It wasn't until 2014 and 15 that the lake levels got really low, and then there was this extended period of time below the natural rim of the lake where there was no water at all flowing in to the Truckee from Tahoe. And we had a decent boost in 2016 that got us above the natural rim, but then even going into that big winter fall of 2017, the lake was still below the natural rim. And this was pretty incredible. I think this was, there's some NWS people here who can correct me, Tim maybe, was the single largest increase in 1 year of the level of Lake Tahoe. Went from below the natural rim, basically full in 1 year. And so you can get that, and we've seen that in some of these other really massive years. 2006 was one, 2011 was another one, so the lake can go from very poor condition to full in just about 1 year if we have one of these really massive winters, which we saw. And so we had quite a bit of decline this summer because we didn't have all the runoff, because we had a pretty poor snowpack. And so we're really hoping for a good winter this year. And I also wanted to show Rye Patch Reservoir, which is out in central Nevada. The Humboldt Basin drains into Rye Patch. This is a very important reservoir for agriculture in Lovelock, which is a big agricultural region in the Great Basin. And this is a much smaller reservoir, and so this takes about 2 or 3 years, or 1 to 2 years to respond, as opposed to 3 or 4 years to respond to these droughts. And so it could fill and it could drain much quicker. And so this was the severe drought we had. 2014 and 15, the lake was basically empty. Summer 2015, the farmers in Lovelock got 0 surface water allotments, which is their main source to irrigate. And so the ag industry in Lovelock was hit really hard during 14 and 15, I think even into 16. And so this is a very important reservoir. And so, again, 2017, it filled up basically completely. And I put these red dots in here. It's hard to see the little tiny blue dots. That these are the latest measurements from the USGS website. And so this was the latest one from this past month, I believe. And so we lost a lot of water this summer, again, because of basically the drought conditions and the poor snowpack and the lack of summer runoff. We only had a little bit of inflow during the summer, and so we lost a lot of elevation in the reservoir pretty quickly. And so if we have another poor snowpack year, there's likely going to be impacts in the Great Basin and the Humboldt Basin due to these much lower levels by next summer in Rye Patch. So now I want to get into kind of what's going on this year at the start of the water year. So our water year starts October 1, and so up here we have our temperatures so far. On the left is October, the right is November. Nothing too extraordinary. I mean, November was pretty warm in California, and the record warm temperatures were actually right around where
campfire started, so that definitely contributed to the drying of the fuels. Throughout Nevada, there are actually some areas of below normal temperatures for both months in the bottom third of the distribution. So most of the Great Basin was kind of near average temperatures. And the precipitation hasn't been too extraordinary yet, nothing too exciting going on. October was pretty dry in the west side and a little bit above normal on the east side of the Great Basin. And November kind of switched around a little bit where the Sierra and Eastern Sierra got some precipitation and it was drier on the eastern side. But most of our beneficial storms for the region have actually come within the last 2 weeks. And we went from pretty much no snowpack in the mountains to above average snowpack, which I'll show some examples of that. And so this is the percent of average precip from November 19th through December 3rd. And so that's when we saw most of our storms so far this year. A 2-week period there that was very active. Green almost across the board with the exception of kind of southern Nevada there. And so that really got our snowpack going. This was from yesterday, the regional snowpack from NRCS. And all the basins, California and Nevada, are above normal, which is really good for this time of year. A better start than last year. But it is still early in the season, and these can change a lot throughout the year. I'll show some curves that show exactly how fast these things can change. And so these are the time series now of the snow water equivalent. This one's for the Lake Tahoe Basin. It starts on October 1 and goes to September 30. The red line is the median, or kind of the normal that we expect throughout the year. And it has the past 3 years on there, which were all fairly interesting. Green is 2018, where we had that big spike in March, but we're still far below normal. By the end, melted out early. 2017 was near record-breaking. Higher elevations in the region saw record-breaking snow. And this is what I mean by how fast things can change. In 2017, January 1, we were still well below normal in our snowpack. And then January and February happened, and the slope of this brown line is really incredible on how fast the snowpack increased in January and February of that year, and got to near record levels. In 2016 was kind of average. And so the black line is 2019, and we're a little bit above that red line right now, but as you can see, things can change really quickly, so hopefully we'll continue the trend throughout the winter. This is the same plot, but for eastern Nevada basins, and a pretty similar situation right now in 2019. They're just a little bit above average for this time of the year. So I wanted to get into the kind of the outlook section and what we can expect over the next few weeks into the next few months, and kind of really know what we can expect over the next few months or not. So in terms of kind of the weather forecast for the next week or so, we really don't have any major storms on the horizon. So this is a this is a precipitation forecast for Blue Canyon, which is on the west slope of the Sierra Nevada. And so this is an ensemble plume, and this is one of the key tools that forecasters use to kind of gauge uncertainty and confidence in a forecast. And so each one of these lines is a precipitation forecast starting this morning and going out 7 days. This is through time, and the total accumulated precipitation throughout that period. And so each one, the model is started with basically observations, and the observations are tweaked slightly with each one of those, just a tiny bit, the temperature or the wind or the humidity. So you have a different set of initial conditions, and that's due to what's known as the butterfly effect. And our atmosphere is very chaotic. It's a fluid. It works like a fluid. It works like a fluid system. And so it's kind of that idea of a butterfly flaps its wings in China. It can change the weather pattern in the western U.S. And so you can see just by changing slightly these initial conditions, you get a wide range of outcomes for the total precipitation. And so this scale goes from 0 to 0.8 inches. So none of this looks like a very big storm at all. But when all the gray lines are close together, you have more confidence in the forecast. And so the first few days looks high confidence that it's going to be very dry. There's a couple of members showing a very small amount of precipitation. When you see this big range of spread between the gray lines, there's a lot less confidence in the forecast because there's all these different ranges of possible outcomes. And so the black line is the mean, and so for this particular outcome, it shows that the mean is about 0.2 inches within the next 7 days. And so again, nothing major showing up there. And this is the same, but for Elko, and we see a very similar pattern, a chance of a small storm going into next week. Climate Prediction Center issues these outlooks for the 6 to 10 and 10 to 14 day periods. And so this is the precipitation outlook on the left from December 11th through the 15th and December 13th to the 19th on the right. And these are probabilistic outlooks, and what these show is the probability or the likelihood of being near normal, below normal, or above normal. And so anything gray, the highest likelihood is kind of near normal. Anything brown is below normal, and anything green is above normal. And so the colors do not tell you anything about the actual amount of precipitation. This tells you there's a stronger chance that you'll be above average. So this kind of bullseye here in the Pacific Northwest is in that, I don't know, 60 to 70% chance of above normal precipitation. It doesn't tell you anything about how much, just there's a stronger chance of being above normal. And so, so for our region, the 11th to 15th, there's slightly favored odds of above normal precip for most of the region, and it decreases even more going into the 10 to 14 day period, where there's still slightly favored above normal odds for the northwest portion, but kind of we don't really know for the central part. I wanted to briefly cover El Nino and Enso, which gets into the seasonal prediction aspect. So with seasonal forecasts, one of the strongest tools to use is Enso, which is a measure. One way to measure it is looking at the sea surface temperatures, and it changes the sea surface temperatures in the central Pacific. And this is a variable that evolves very slowly compared to the land surface and the weather patterns. And so it has memory, and it can actually be used as a tool to forecast several months in advance. And so what Enso is, it's a pattern in the central Pacific Ocean. And so this is a cross section along the equator of Darwin, Australia, Lima, Peru. And so it's a coupling of the atmosphere and the ocean patterns. And so this is the typical situation where you have the Walker circulation, the trade winds blowing from east to west, and then you have the oceanic circulation, strong convection, lots of thunderstorm activity in the western Pacific, and upwelling of cooler water into the eastern Pacific. In an El Nino pattern, this shifts and the trade winds weaken quite a bit, and you have stronger westerly wind bursts, and the thunderstorm activity is shifted more to the central part of the Pacific, and the upwelling in the east is weakened, and so you have more warmer water in the central and eastern Pacific, and La Nina is basically an enhanced phase of the normal pattern where you get more cooler water in the Pacific. And these patterns show up really nicely when you look at maps of the sea surface temperatures. This is a strong El Nino from 1998. You can see lots of warm water. And when you look at the anomalies, you can see well above average sea surface temperatures along the Pacific there. And this is a La Nina event where you see the blues indicating the sea surface temperatures are cooler than average. And so this can all lead to due to different levels of moisture and where the moisture is actually put into the atmosphere, linking to how our weather patterns in the western U.S. are actually affected by these patterns. And so there's a kind of a typical pattern of El Nino and La Nina in terms of storm track. I put typical in quotes because we're in a region here. Did I highlight that? Yeah, I did. So we're kind of right here. The top is an El Nino pattern where you have a very strong subtropical jet stream and more moisture in the southern tier and drier in the north. And it's kind of reversed with La Nina, but we're in this kind of really in the white area where there's no really strong signal one way or the other, whether it's going to be wet or dry. Although El Niños are typically warmer, that's the one kind of consistent signal. In terms of where we are right now, we were in a very weak La Nina last year, and throughout the summer the sea surface temperatures have been warming. These are the different Nino regions. It's kind of hard to see, I apologize, but this is the Central Pacific and the different Nino basins, but they've all been warming throughout the summer. Based on the Climate Prediction Center, we're still in Enso neutral conditions, but there is an El Nino watch currently issued. And it does look like we're going to go into at least a weak El Nino. And so these are probabilities for each season of going into El Nino. And so this is October, November, December, January. And so these red bars are showing greater than 80% chance of transitioning to an official El Nino, although it doesn't look to be like a strong event at all. I'm going to probably show one of these and then skip a couple because I'm running out of time here, but just the fact on how little kind of we really know just by the Enso state in terms of precipitation for the region. This is for the northwestern Nevada region, and so on the x-axis we have the strength of the El Nino or the La Nina, where to the right is stronger La Nina, to the left is stronger El Nino, and then on the y is the total precipitation from October through March. And the black line here is the mean of all the values. And so it's basically a shotgun scatter there. The R squared is 0.01. There's no relationship whatsoever. Our wettest year on record was Enso neutral, neither La Nina or El Nino. Our driest year was Enso neutral, and there's a lot of dots on both sides of the black line. And so for this region, Central California into Central Great Basin, there is not a strong relationship at all with Enso in terms of precipitation. So these are a couple of the same plots. This is for Eastern California, again, no relationship. Southern Nevada, as you go further south, the relationship becomes a little bit stronger. So the R squared here is 0.21. The La Ninas tend to be a bit drier, and the El Ninos tend to be a bit wetter, but it's not a very strong relationship. So on to the final outlook for December, and then the winter outlook. These are issued by the Climate Prediction Center. This is the December forecast, and again, these are the probabilities. So the Great Basin here for December, the eastern part has higher odds of being below normal temperature-wise, and the western part above normal and kind of 50-50 in the middle. And there is a stronger signal for above normal precipitation for December. The western part of the Great Basin is greater than 50% chance of being above normal, and the rest of the Great Basin, a little slightly lower odds, but still favored to be above normal precipitation-wise. And then this is the winter outlook going from December through February, same maps. And this is kind of showing that typical El Nino pattern that I was showing before that's being favored by the forecasters. Warm conditions, higher odds of warm conditions, and stronger odds of wetter conditions in the southern tier, although the odds are lower. Not a very strong signal. And my last slide, so this is a very similar outlook. This is from the IRI, the International Research Institute at Columbia, who works with the CPC a lot on forecasting, and they put out their own outlooks. I believe this one is only based on the numerical models, whereas the CPC, they use their judgment to come up with those forecasts as well. But it's different than the CPC outlook. They're showing a strong pattern of higher than normal odds for cool temperatures in the central U.S., and actually some odds of wetter conditions in the Pacific Northwest, where and kind of equal chances in the south. And so, the bottom line with the seasonal outlooks is, I hate to show this, but you really just don't have a strong sense of what's going to happen that far in advance. You can look at the guidance. I strongly suggest paying close attention to weather forecasts and those monthly forecasts out to 1 month give you a good sense. we really just don't have a good sense of what to expect this spring.